Okay, well, you know how one project leads to another project. I was working on a project which I think I'll film, but I needed a box to put the project in, and I kind of collect old things or buy them when they're only a buck or two or something, just to use the case, you know, rip out the electronics and reuse the case. So that's what I did. I had a case, a piece of electronics with a nice case, and I opened it up to strip out all the electronics, and this is what I found inside. And I thought, oh well, this might make a really interesting project for YouTube. It's a 8085 single board computer, and it's not. This is a 25 pin connector, but it's not serial. It's a parallel interface, and this is what people used to have to do before there was microcontrollers. There were microprocessors, but there weren't microcontrollers until much later. So this board was designed around 1979, 1980. There's some pen mark. I don't think you can see it, but there's a pen mark on the back of the board where whoever tested this board wrote on it. It says 1981. So the board was shipped off in 1981. So this is definitely vintage, and this is an embedded system. All it had to do was talk to some parallel pins, and there is an 8085. Now the 8085 came after the 8080. The 8080 was a little difficult to use because it required 3 voltages. It required +5, +12, and I think -12. And it required a clock chip. We saw that when I was redoing the IMSAI 8080. I needed a clock chip. I think I ordered it from Eastern Europe someplace. So there was a few things that were a little bit difficult to use the 8080. So they came up with the 8085. The 8085, first and foremost, was a 5-volt part. All you had to do was give it 5 volts, which is great. They also got rid of the clock chip, so you just put a crystal on the chip and it would run. So it was much easier to run. I think the reset circuit is easier also. This one has a capacitor over here for the reset. So let's just take a look at the board here for a second and try to figure out what all these chips are. So obviously there's the microprocessor, the 8085. Now you need ROM and RAM. Any application you need ROM and RAM. So we can see the ROM chip right here. There's a 2716, which was kind of like the chip in the day. This is a 2K by 8, optically erasable. So there's a window here under this tag, and you shine UV light on it to erase it, and then you could program it. So we have 2K of ROM. Here's our RAM. These are 2114. So these are 4K by 1K. So this is 4 bits. And this is 4 bits, so we have 8 bits by 1K. So we have 1K of memory, 2K of ROM, 1K of memory. Now we need some I/O. That was the whole thing about a microcontroller. You're trying to control things. You need an interface. The old microprocessors, they were just a bus. They didn't have I/O. You had to add I/O to it. So here's an 8255. So this should be familiar with the Zeta board. The Zeta board uses an 8255, and this would add 3 8-bit ports. Now this particular implementation, they only used the A port. They only used 8 bits of this thing. They needed to get I/O, and this is a very simple chip to use and probably fairly inexpensive, so that's what they used. And they didn't use the B port or the C port. Kind of wasteful, but they just used 8 lines. And those 8 lines run over here to this connector. So that's all this board could do, is talk to these 8 lines. So what is this big chip over here? Well, remember that the bus on the 8080 is multiplexed, so it uses the address and the data on the same pins, and you need to latch the address. The higher address bits, that it's a 16-bit address space, but only an 8-bit data bus. So the upper 8 bits of address come directly out of the 8085, but the lower 8 bits of address need to be demultiplexed and latched, and that's what this is. This is an 8212. Today we wouldn't even bother using this chip. We would probably use a 74LS 573, which is an octal latch. So much more modern part, but this was the original part that Intel came up with when it introduced this chipsets. It said, here you go, if you need to demultiplex the address bus, go ahead and use our 8212, we'll sell that to you. So that's what this does. So we've identified all of these chips. There's a chip up here that's just a 7414, and the 7414 is a Schmidt input inverter, and I believe that's probably just used as part of the reset circuit. It allows you to get a very clean reset. When this capacitor starts to charge up, it'll fire the Schmidt input, the hysteresis on the 7414, and reset the chip. It does have a crystal. This is a 5 megahertz crystal, so this is a 5 megahertz computer. And then there's some chips down here at the bottom, and one of the things that we need to add is a way to place chips in memory. There are chip selects on these chips, so you need to locate them. So you need some address decoding. And so some of these chips down here are being used for the address decoding. They probably address the ROM at 0, because when the microprocessor starts up, it goes to the address 000. And so the ROM probably is at 0. The RAM is probably someplace up in memory somewhere. So that's decoded here in the bottom. And the 8255 has a chip select. You need to place that somewhere in memory. So there's a chip select that comes off in there. So I'm not quite sure what all of these chips are doing, but they certainly are performing part of the address decoding. There's an interesting chip over, well, let me just tell you what these chips are. There's a 7474, which is a D flip-flop. I can show you some scope traces, but I know that the signals run over here into this D flip-flop. It's a dual D flip-flop. And 2.5 megahertz comes, 2.5 megahertz clock comes into here. So I believe that the 8055, it's a 5 megahertz clock, but it outputs a clock at half of that, so it's outputting a 2.5 megahertz clock. It gets divided once, and so there's a 1.25 megahertz signal available, and then it gets divided one more time down to 625 kilohertz. And I believe that was for some circuit here that isn't loaded. So this is some other chip, or it's an expansion connector that goes off to another board. I don't know what this is. It's labeled U11, but it doesn't say what it is. But those two clocks, at least two of them, the 2.5 megahertz and the 1.25 megahertz, are available on this chip here, or this connector. It's just a connector. So this is what you would have to do. This would just be replaced by a single microcontroller now, just a single chip. But this is what you would have to do to develop a board for an embedded application. All right, let's apply some power. I've got ahead and added a couple pins here that I know what they are. This is the ground pin and this is the 5 volts pin. So we'll connect 5 volts to this thing and see if we can't probe around on this thing with an oscilloscope and see what's going on. So can I get both of these in the picture at the same time? Let me move the camera around. Okay, you won't be able to see the board while I'm probing it, but I'll just have to tell you where I'm probing. So I'm hooking up the ground lead of the scope probe, and I'm just going to take a look at the crystal. And we can see a clock here, and let me measure the frequency. Frequency is 5 megahertz. Okay, so that's what's on the crystal. And like I said, one of the clocks down here. Let's see what this one is. Yeah, this is a 2.5 megahertz signal. So that's available on that U11 that's missing. There's another clock here, which is a 625 kilohertz, so that's been divided twice. So for whatever reason, this chip had slower clocks available. Don't know what they were used for. Let's take a look at some data lines, just for fun. See if we see anything on the data lines. Now there's something. And let's take a look at another data line. There we go. So it's obviously running a program. Let me do a single on it. So every time it seems like it's always coming up with the same data pattern. Let's take a look at another data line. There's one. Sorry, my hand's in the way. Oh, there we go. That's a nice signal. Let me put it on normal. So I think I can just... the scope doesn't work that way. Interesting. Oh, well. You can tell that it's running, though. It's running a program. So one of the nice tools back when I was developing boards like this, I developed a lot of 8085 single board computers back early in my career, and the development systems were very nice. You could unplug the 8085 and plug in this big monstrosity of a machine, and it would pretend to be an 8085, and you could take a look at all of the addresses and all the data, and you could set breakpoints, and you could load programs, and you could examine everything. They were very powerful tools, very expensive tools, very powerful tools. Be nice to have one of those to show you here, but I just don't. We could take the EEPROM out and take a look at the program, but I don't think that'd be very interesting. But I think the interesting thing would be is to take a look at some single board computers that other people have developed online using the 8085 and kind of give you an idea of what was done in different designs. Everybody kind of did their own thing, but they're very, very similar. There's ROM, there's RAM, and there's I/O. And the 8085 was very simple to design a board around.